Have you ever really thought about what you're seeing when you look up at the night sky? It's not just a bunch of twinkling lights. It's a cosmic factory, busy creating the very stuff that makes up our world. But sometimes that stardust gets here with a bit of a mystery attached. And today, we're going to dive into one of those puzzles, the incredibly strange physics of how liquid carbon freezes out there among the stars.
So, here it is, the central question. For years, scientists have been finding these microscopic spheres of pure carbon tucked away inside ancient meteorites. This is literal stardust. The catch? When we try to make these exact same spheres in the lab, they just don't turn out the same. Something's going on in the atmosphere of a dying star that we haven't been able to copy. So, what's the secret ingredient?
And this slide really puts the mystery right in front of you. On one hand, you've got the stardust from meteorites. It cooled really slowly out there in space, and its internal structure is pretty ordered, with these big, beautiful sheets of graphene. But then, on the other hand, there's our lab-grown stuff. We cool it down super fast, and we get this chaotic mess of tons of tiny little sheets. It's the same element, carbon, but two totally different outcomes. Why?
To solve this, our first step has to be examining the evidence. We need to take a really close look at these tiny messengers that have traveled across the galaxy to get to us.
You can think of these little spheres as perfect time capsules. Seriously, they started out as tiny droplets of liquid carbon floating around in the atmosphere of some ancient star, way back when. They condensed, they solidified, and then they journeyed through the cosmos for who knows how long before finally crash landing on Earth inside a meteorite. They're a direct snapshot of a process that happened light years away and millions of years ago.
So, you might be thinking, okay, why not just watch liquid carbon freeze in a lab and see what happens? Well, that's a great question, and it brings us to the next part of our story. Turns out, liquid carbon is incredibly hard to work with. It's one of the most elusive materials in all of science.
Because getting carbon to even become a liquid requires some absolutely mind-bending conditions. We're talking extreme pressure and temperatures of around 4,600 Kelvin. That's almost as hot as the surface of the sun. See, at normal pressures, carbon doesn't even bother with being a liquid. It just goes straight from a solid to a gas. It sublimates. So to study it, scientists have to resort to some pretty wild stuff, like blasting graphite with super high-powered lasers just to get a fraction of a second's glimpse of it in liquid form. It's like trying to photograph a ghost.
This brings us right to the core physics of the whole problem. Because even if you manage to make liquid carbon, getting it to freeze like stardust involves a really weird transformation. The issue is really a question of dimensions. Picture this chaotic 3D soup of carbon atoms swirling around. For this soup to freeze, the atoms can't just lock into place like water freezing into a 3D ice cube. Nope. They have to completely rearrange themselves into these perfectly flat, two-dimensional sheets of graphene. That's a huge structural and energetic hurdle to overcome.
So the process unfolds in three basic steps. First, you've got your 3D droplet, that soup of liquid carbon. Then, just by random chance, a few atoms, like 5 or 6 of them, click together into a stable little ring. That's called nucleation, and it's the seed for a brand new crystal. And finally, you get growth, where other atoms in the liquid latch onto the edge of that seed, expanding it outwards into a bigger and bigger 2D sheet.
Okay, so we have all the pieces on the board now. We've got the mystery of the different structures, the challenge of working with liquid carbon, and this weird 3D to 2D freezing process. It turns out the solution that ties it all together is beautifully simple. It all comes down to a single variable, time, or more specifically, the speed of cooling.
This quote from the research paper just nails it. The whole game is to explain why slow-cooled stardust gets those big, orderly sheets, while our fast-cooled lab carbon is just a jumble of tiny ones. And the answer is basically a race, a competition between how fast new crystal seeds can form versus how much time those existing seeds have to grow. Right, so in the super slow cooling environment of a star's atmosphere, the temperature drops very gradually. This creates this perfect window of opportunity. It's still warm enough for atoms to easily find and attach to existing seeds. That's a high growth rate. But it's not quite cool enough to trigger a bunch of new seeds to form, so you get a low nucleation rate. The result? The very few seeds that do form have all the time in the world to grow into these massive graphene sheets.
Now, flip that completely on its head for the lab. Here, we're cooling it down incredibly fast. As the temperature plummets, the liquid hits this point where nucleation just goes crazy. Bam! Thousands of seeds pop into existence almost all at once. But because we're cooling it so fast, there's basically no time for any of them to grow before the whole thing is frozen solid. It's like a traffic jam of countless tiny, stunted crystal sheets.
You know, there's a really simple way to think about this. It's just like making rock candy. If you cool sugar water nice and slow, you get those big, beautiful, chunky crystals. But if you take water and flash freeze it, you get cloudy ice, which is cloudy because it's filled with millions of tiny microscopic ice crystals. It's the exact same principle, just happening with Stardust.
So, mystery solved. Cool, right? But what's really amazing is that in the process of solving the Stardust puzzle, the researchers uncovered something even more profound about the fundamental nature of carbon, something with huge implications way beyond just astronomy.
Take a look at this number, 50%. What in the world does that mean? Well, this number is the key to an even bigger discovery that came out of all this. It reveals just how fundamentally weird carbon is and points to a world record it holds in material science.
This is what that 50% is all about. It means liquid carbon can be cooled to half its freezing temperature and still stay liquid. This is a phenomenon called deep supercooling, and that 50% drop is a record for any pure element. It just resists freezing more stubbornly than anything else we've ever found. It's wild.
And why can it do this? Well, it all comes back to that crazy dimensional leap we talked about earlier. See, a typical metal freezes from a 3D liquid into a 3D solid. That's a pretty easy transition, structurally speaking. So they can only supercool by about 30%. But for carbon, that difficult jump from a 3D liquid to 2D sheets is so demanding that the liquid can be pushed to these extreme cold temperatures before it's finally forced to give up and solidify.
So what's the big takeaway here? Well, this research does a lot more than just explain Stardust. It fundamentally changes how we understand the behavior of carbon. And by mastering this process, by learning to control these cooling rates, we might be able to create entirely new kinds of carbon-based materials right here on Earth. Materials with properties we've never even seen before, like composites made from unlayered graphene.
And that leaves us with one last really fascinating question. For thousands of years, we've built our world with carbon, in the form of wood, diamond, graphite. But now, for the first time, we're starting to understand the secrets of its liquid state. We've cracked the code of the cosmic factory. So the question is, what's next? What incredible things are we going to build now that we know how?